Okay, vectors. Let's say we have these two vectors. And by vectors, we just mean this quantity with a magnitude or length, a size, and a direction it's pointing. For example, this vector would be a magnitude of 10 meters and a direction usually listed as an angle of 60 degrees. And let's label these. Let's call these, let's say this is vector R1 and vector R2. And we often call distance vectors, like a vector referring to a distance from some place to another place, as r, standing for radius. Because if you think of this as let's say, a vector on an xy plane, typically with the vector at the origin, then the vector, if it's a distance, really is just a radial distance outward from the origin. Radial in the sense of distance outwards from the center. So we're often going to refer to distances vectors as r. And if you want to take these vectors and add them together, if we wanted to write out r1 plus r2, and by the way, in formally the notation should have a little arrow or sort of a half arrow written over each one of these. I'm not necessarily going to write the arrow over each one in computer text because that's kind of inconvenient to do. But in writing, each vector sign should have, or each variable representing a vector should have its little vector arrow sign over it to represent this is a vector. Sometimes in text, in printing, that's done in bold instead of with a vector sign, but it means the same thing. And that basically just means that R1 isn't just the number 10. R1 is the number 10 and the direction 60 degrees above horizontal. And we typically do measure vectors or measure directions relative to a horizontal like this. So when we say 60 degrees, we mean this angle. When we mean 15 degrees, when we say 15 degrees, we mean this angle. So generally assume that angles are measured from the horizontal, from the positive x-axis, counterclockwise unless specified otherwise. Any questions on the terminology there so far? So if we wanted to add these vectors together, let me make some copies of these just to make it easy to move around. If we wanted to add vector R1 plus vector R2. Can we just add 10 plus 4 and get 14?
No.
Not in this case. You sometimes can. Are there any circumstances in which you can just add the magnitudes of the vectors?
When they're in the same direction?
Yeah, if you've got two vectors that are exactly in the same direction, let's say you've got like this vector and this vector. If they're exactly in the same direction, and let's say this one's 5 meters long and this one's 10 meters long, you would just add 5 plus 10 and get 15 meters in this direction. But that only works if they're in exactly the same direction, if they're parallel to each other. More generally, if you want to add two vectors together, you can think of it as, I usually think of this as being like a set of directions. If you want to add two vectors together, R1 plus R2 basically is, R1 says go this far in this direction, R2 says go this far in this direction. So you're basically following these directions sequentially. From where you start, let's say this is just the origin of an XY plane. So here's the x-axis, here's the y-axis. The idea is that we are taking the origin as the starting point, because you can move a vector anywhere. A vector doesn't really have a location. It just has a size and a direction. So you can move the vector anywhere you want. And you can say, let's say this vector represents from where you start, travel 10 meters in this direction. And then R2 says from where you are now, travel another 4 meters in this direction. And what we care about for the vector sum is the total of those together. In other words, where it takes you from the original starting point to the final ending point. So this is what we mean geometrically by R1 plus R2. R1 plus R2 is the result of following vector R1's directions from some starting point, and then following R2's directions from the same starting point, or from the new starting point. This is often referred to as putting the vectors together head to tail. And then R1 plus R2, the sum, or sometimes called the resultant vector, just the result of adding them together, is a straight line vector from the original starting point to the final ending point. Basically just describing how far you'd have to walk and in what direction to do all that in one step to get to that same final ending point. Any questions on that so far? By the way, what if we were adding these in the other order? What if we had R2 plus R1 instead? What would that mean differently? Or what would we be doing?
Would be in a different order, but they give you the same answer.
Yeah, if you add these in a different order, let me make a couple more copies of this. If you add these in the opposite order, let's say you start with R2. So from the origin, you follow direction R2 for that far. And then from that as your new starting location, you follow R1, but you still end up in the same location. So order does not matter when you're talking about adding vectors together. You can add R1 plus R2, or you can add R2 plus R1, you get the same result. Any questions on that so far? Also for subtracting vectors, let's say we're trying R1 minus R2. If you want to write out R1 minus R2, how would you interpret that? What does that mean? Like R1 plus R2, you could just think of it as walk this far, and then from that location, walk this much further. But what would you expect R1 minus R2 to mean? Yeah, or not so much rotate it, but really more reflect it. Because if R2 is 4 meters to the right and a little bit up, negative R2, because you could always write the R1 minus R2 as R1 plus negative R2. Negative R2 is just the same distance, but in the exact opposite direction. So negative R2 would be this vector. And then R1 is still exactly the same. Let me make another copy of that. So one way to think of subtraction is just adding the opposite. R1 minus R2 is the same as R1 plus negative R2. So you can still think of this as addition. We're just adding them, or adding the first vector plus the opposite of the second vector. And this is generally what a negative multiplier does to a vector. Note that a vector on its own doesn't have a sign. A vector is neither positive nor negative. A vector has a direction rather than a sign. So we wouldn't like say that R2 is a negative number or R2 is a positive number. R2 is just in the 15-degree direction. But negative R2, that negative doesn't mean make this a negative value. The negative means take the opposite of. And the opposite of a vector means the same magnitude, but the exact opposite direction. So you could kind of describe that as rotating specifically by 180 degrees, but I think it's really more accurate to represent it as a reflection. We're flipping it over from to a mirror image of what it was. And then the sum of those, R1 plus negative R2, would again just be the straight line vector from the starting point to the new ending point. So we could interpret R1 plus negative R2 as this vector. So that's definitely one way to do it. You can always rewrite subtraction as adding the opposite. But there's another way of thinking of vector subtraction that I think is much more meaningful, especially if you're talking about deltas. If you think of, let me put this off to the side. Another way to think about R1 minus R2, R1 minus R2, you could think of that as delta R, the difference in position. Because these R vectors are basically representing position. Like R1 could be thought of as traveling some distance, or you could think of R1 as labeling a location that's 10 meters away from the origin. These R vectors are basically describing positions in space. So if you think of R1 minus R2 as a delta R, usually how do you calculate delta anything?
Final minus initial.
Yeah, final minus initial. So you could interpret this as thinking of R1 as a final position and R2 as an initial position. R1 is the final position, R2 is the initial position. So we get just R final minus R initial. So you can always think of, anytime you're subtracting two different values of the same quantity, you can always think of that as possibly representing a final minus initial sort of change. So if we look at it that way, we're basically looking at the difference between two positions. So going back to the idea of, let's say, the origin on a graph, instead of putting these vectors together head to tail, let's make another copy of, let me just borrow these ones, I guess, R1. And then if we put R2 at the same origin, so R1 and R2 can be thought of as just describing two different locations relative to the same origin point. Then R1 minus R2 could be thought of as the change from R2 to R1. Again, if you think of this as final minus initial, that means imagine we're starting at location R2 and moving to location R1. That's just going to be this change. So R1 minus R2, or anytime you're subtracting vectors, it's very useful to think of that as a difference, the change from initial to final. In this case, the change from R2 to R1. And you can draw that quite easily by just putting both vectors drawn from the same starting point. So both vectors coming out of the same starting point. And then look at the difference. What do you have to do to change change R2 into R1? If you start with R2, you change it into R1 by stretching it or moving it along this change vector. So that would be delta R in this case. R2 minus R1 minus R2, final minus initial. And this is a very useful way of thinking of any subtraction that represents a difference. Like this arrow here, it literally is just the direction you would travel and how far you would travel to go from location 2 to location 1. If R2 and R1 just represent locations on a graph or locations on a map or in space or something, delta R is how far you travel and in what direction to get from one place to the other place. Any other questions on that so far?
Does it matter which direction the arrows go? So like this past example with the one on the left, the arrows are like in opposite directions.
With this one, when we're talking about subtraction?
And when you find the difference.
Yeah, for addition, order doesn't matter. R1 plus R2 is the same as R2 plus R1. But for subtraction, it matters which one is being subtracted. So R1 minus R2, you're taking R1 exactly as is and adding the opposite of R2. If you did that in reverse, if you took R2 minus R1, you'd be keeping R2 exactly as it is. R2 exactly as it is, but then taking the opposite of R1. So if you wanted to draw R2 minus R1, that'd be R2 in the usual direction plus the opposite of R1. So that would look more like this. This would be R2 minus R1, whereas this one we looked at before was R1 minus R2. And you could still think of that as a difference. It's just the difference that takes you from R1 to R2 instead of the difference that takes you from R2 to R1. So the only difference between these is which order we're subtracting, which one we think of as final and which one we think of as initial. So if you have R1 minus R2, that means R2 is initial and R1 is final, final minus initial. So R1 minus R2 is the vector that takes you from R2's location to R1's location. Whereas R2 minus R1 would take you from R1's location as initial to R2's location as final. And note that these delta vectors, R1 minus R2 and R2 minus R1, they're the same magnitude, but just opposite directions. Same size, but opposite directions. Any other questions on that so far? One other thing about magnitude. Let me clear these away for the moment. If you're adding a vector whose magnitude is 10 and a vector whose magnitude is 4, but let's say you're allowed to change the direction. So let's say you've got a vector whose magnitude is 10, but you're able to swivel it around to any direction you want. And you've got another vector whose magnitude is 4, but you're allowed to swivel it around to any direction you want. If you wanted to get the largest possible result from adding them together, what direction should you choose? If you wanted to make R1 plus R2 as large as possible. Yeah, if we're allowed to change the directions, then we can just make these the same direction. If this is 10 and this is 4, and they're the same direction, what would you get if you add them? Right, 14. So the 14 would be the largest these vectors could add up to. And of course, in this case, they won't actually add up to 14 meters because they're not in the same direction. But 14 is the hypothetical maximum you can get from adding a 10-meter vector plus a 4-meter vector. So we know R1 plus R2 is going to be less than or equal to 4. Or actually, let me make this more clear. It should be absolute or magnitude of R1 plus R2. This double absolute value bars is the symbol we usually use for magnitude of a vector. So, and magnitude just essentially is absolute value for vectors. It means how big is it without caring about direction. So we'd say magnitude of R1 is 10 meters. Magnitude of R2 is 4 meters. Magnitude of R1 plus R2, which really should have little vector signs over it. Magnitude of R1 plus R2 can't be more than 14. It's got to be less than or equal to 14. And also magnitude is always a positive value because it's essentially the absolute value for vectors. So 14 is the hypothetical maximum. What about a hypothetical minimum? How could we swivel these around to get the smallest possible magnitude? If we can make these vectors in any direction we want. Yeah, if we make them in exact opposite directions. If we're adding R1, 10 meters up and to the right, plus R2, 4 meters down and to the left. Again, we could put these together head to tail. And then the sum, R1 plus R2, would be this vector. So this would be R1 plus R2 from the beginning of the first vector to the end of the last vector. And then how long would that be if R1 and R2 happen to be in exact opposite directions? We got 10 in one direction and then 4 in the exact opposite direction. So what do we get? Right, that's just going to be 6. So that's the hypothetical minimum value for R1 plus R2. R1 plus R2 has to be greater than or equal to 6 in this case. So this puts some limits on it, some boundaries. Without even adding together these vectors yet, we know that the result can't be bigger than 14 and also can't be smaller than 6. It's going to be somewhere in between those. Any questions on the geometry there so far? So with those limits in mind, that it can't be less than 6 or more than 14, let's try actually adding these. We could use this triangle here. We know we're setting it up as R1 plus R2 added together head to tail. One way we could accomplish this is by figuring out some of the angles involved. If we figured out, for instance, this angle, then how would we find that angle? Or could we find that angle? How would we do that? I guess it might be easier to find this angle, because we can find that by combining the 60 and the 15. For instance, if we draw a straight line here, we know this is 15. We know this is 30 and this is 90. So we could add those 30 plus 90 to plus 15 to get this angle. We know this side is 10, this side is 4, and we can find this angle. So it's possible to use some advanced trigonometry techniques to find the missing side. Since we've got side angle side, I think law of cosines would work, or maybe law of sines. But fortunately, we don't actually need to resort to the advanced trigonometry stuff. We can do this entirely using just right triangles by drawing out the components. The idea is we're going to split each of these vectors into components. You could describe the R1 as turn in the 60-degree direction and walk 10 meters forward. But you could also get there by walking a certain distance to the right or to the east and a certain distance to the north. That the R1 vector, it doesn't have to be go 10 meters in the 60-degree direction. You could go a certain distance to the east and a certain distance to the north, and you get to the same point. Or to put it another way, any location on a graph you can label as how far it is from the origin and in what direction, or you could just label it as an x component and a y component. So let's see if we can find those x component and y component. We're going to call these R1 sub x and R1 sub y. And we want to find those as ideally numerical values. But how could we do that? Now that we've established a right triangle using the vector itself as the hypotenuse, and we're trying to find these legs of the right triangle, x component and y component, how could we do that using this 60-degree angle? What trigonometric functions would be useful here? For instance, let's say we wanted to find the y component. How would you describe the y component relative to the location of the angle? Yeah, this is going to involve sine, right? Because the y component is opposite to the angle, and sine of an angle is opposite over a hypotenuse. In general, if you're talking about right triangle trigonometry, right triangles, sine of the angle is opposite over hypotenuse. Cosine of the angle is adjacent over hypotenuse. And tangent of the angle is opposite over adjacent. So anytime you're dealing with knowing the hypotenuse and wanting to find the opposite side, you can use sine of the angle. So let's write that out. We can say that sine of 60 degrees is opposite side over hypotenuse. And then how would you solve for that opposite side? Yeah, we just multiply both sides by 10. And I would say specifically multiply both sides by 10 meters because we want to keep the units intact. So 10 meters times sine of 60. And sine of 60, if I remember correctly, is just root 3 over 2. So we get 10 meters times root 3 over 2. the over 2 and the 10 reduce to just 5. So we get 5 times root 3 meters. Or if we want a decimal approximation, we can punch that into a calculator and get 10 times sine 60 is about 8.66. And we'll keep the units on that. That is still measured in meters. Any questions on that so far? And what about the x component? How would we find that? If we're trying to find the adjacent side, what would we do differently? Yeah, we could use cosine. It's the exact same process, cosine of 60 degrees. And then cosine is adjacent over hypotenuse. So that'll be R1x divided by 10 meters. And then we do the same thing. We just multiply both sides by 10 meters, the magnitude. And cosine 60 should just be 1/2. So we just get 10 times 1/2 will be 5 meters. So that's R1x. And they're not always going to work out to nice, neat numbers if you don't have certain specific angles. Some good ones to know are 30 degrees, 60 degrees, and 45 degrees. 60 degrees is convenient because a 60, 30, 90 triangle forms exactly half of an equilateral triangle. If you just double this, if you reflect it across the long side, this is an equilateral triangle. So what do you know about all of its sides? If it's 60 degrees, 60 degrees, 60 degrees, all the sides are what? Yeah, they're all going to be 10 meters. But then if you slice that in half to make a 30, 60, 90 right triangle, this short leg is going to be exactly half of the hypotenuse. So this is something useful to keep in mind. Anytime you're dealing with a 30, 60, 90 triangle, the short leg is exactly half of the hypotenuse. And then the longer leg you can find using the Pythagorean theorem, and that ends up being root 3 over 2 times the hypotenuse, or root 3 times the short leg. So 30, 60, 90 triangles are very convenient for that. And from that, you can find the sine and cosine of 30 or 60. For 60 degrees, the cosine is always 1/2, and the sine is always root 3 over 2. For 30 degrees, it's just the reverse. Sine is 1/2, cosine is root 3 over 2. So those are very good ones to know because A, they're fairly straightforward numbers, so it's pretty easy to memorize, or even to derive from scratch just by drawing out an equilateral triangle and cutting it in half. And 30 degrees and 60 degrees show up often enough that they're worthwhile to just know. And likewise, a 45, 45, 90 triangle. If you got 45 degrees, 45 degrees, 90 degrees, what do you know about the size of that triangle? If the angle involved is exactly 45 degrees, what does that tell you? If this angle is 45 and this angle is also 45, what does that tell you about these two legs? Yeah, those short sides are root 2 over 2 times the long side. Specifically, they've got to be the same. Even if you don't remember the root 2 over 2 stuff, we know that the two legs have to be equal to each other because this is an isosceles right triangle. 45 and 45 are the same. And then the hypotenuse is just going to be square root of x squared plus x squared. So if you actually use the Pythagorean theorem on this, you find that the short sides are square root of 2 over 2 times the long side, which means sine and cosine of 45 degrees are both root 2 over 2. So those are good ones to know. 30, 60, and 45 degrees all have very convenient, nice, neat, tidy sines and cosines. So those would be good to just memorize or know how to derive from these special triangles. Any questions on the trigonometry so far? All right, so so we can label this. We can now say we can label R1 in terms of its XY components. R1 is, and we sometimes write these in parentheses or sometimes angle brackets, just the X component and the Y component, separated by a comma. And you could write it as 5 meters, comma 8.66 meters, or 5, comma 8.66 meters. Essentially, we're factoring out the units. So vector R1, I should really draw a vector sign on that. Vector R1 can be described as 10 meters in the 60-degree direction, or vector R1 can be described as 5, comma 8.66 meters. Two different ways of describing exactly the same thing. And one of the convenient things about this is as long as you're using what's called standard position for the angle, as long as your angle is just from the positive x-axis measured counterclockwise. So from the positive x-axis measured counterclockwise from there, as long as you're always using that angle, then the x component will always involve cosine and the y component will always involve sine. So we can do that for R2, for instance, if we wanted to find these missing sides. This side, let me make that more visible. If we wanted to find this side length and this side length. And keep in mind, you want to draw the others, you want to treat the vector as the hypotenuse, the diagonal, and then drawing the other sides that are one side that is completely horizontal and one side that is completely vertical. Because you want to form a right angle and nice, neat x component and y component. So to find those components, R2x and R2y, we could just jump directly to the sine and cosine. You could, of course, set it up if you need the extra steps. But as long as you're measuring the angle from the positive x-axis counterclockwise, the x component will always be involving cosine, specifically magnitude times cosine of the angle. And the y component will always involve magnitude times sine of the angle. This out of the way. So punch those into a calculator or look it up on a trig table. Sometimes the old ways work well. 4 times cosine of 15 is about 3.86 meters. And 4 times sine 15 is about 1.04 meters. So that means we can write R2 in terms of its components here as well. We can say R2 is x component comma y component. So 3.86 comma 1.04 meters. So that is the description of vector R2 in terms of its components. Any questions on those so far? And the nice thing about this is it makes it very easy to add the vectors together. Ostensibly, the whole point of finding x and y components is that we can now find R1 plus R2 very easily and very accurately. If we want to write out the sum here, the sum of vector R1 plus R2, how do we do that? How do we add these vectors now that we've got x and y components? If we draw those x and y components on this big picture, we've got R1 is 5 to the right or 5 to the east and 8.66 to the north. Vector R2 is 3.86 to the east and 1.04 to the north. So if we want the x and y components of this big lavender vector, the sum of both of them, how would we do that? How would we combine this information? Yeah, we can add the x components because check this out. If we take the x component of R2 and I just drop that down here, that's R1x plus R2x. And then if I take the y component of R1 and just slide it over here, I'm not changing the length, I'm just moving it around. So we've got R1x plus R2x is the new x component of that big lavender vector. So R1x plus R2x is the actual R1 or Rx value. And then R1y plus R2y is the total y component of the sum. So this geometrically is why we can just add together the components. X component plus x component equals the total x component, y component plus y component equals the total y component. And this is very convenient because it means that by splitting them up into components that are perpendicular, those components don't really interact. We can look at just the x components on their own without having to worry about the y components. And also we can look at the y components on their own without having to worry about the x components. So adding those, we got 5 plus 3.86 is 8.86. 8.66 plus 1.04 would be 9.7. So this is the value of R1 plus R2. R1 plus R2 as a vector has components 8.86, 9.7. So now we know those values, at least the x and y components. Any questions on that vector addition so far? And of course, subtraction works the same way. If you wanted to subtract R1 minus R2, write them as components, and then just subtract components one at a time. 5 minus 3.86, 8.66 minus 1.04. This is also convenient for multiplying a vector. If you're multiplying a vector by a scalar, scalar just being a number without a direction, like let's say you're multiplying R1 by 3. Multiplying R1 by 3 should just triple its length without changing its direction. So 3R1 would just be 30 meters in the same direction. But you can also treat that as multiplying each component by that scalar. So 3 times R1 would have components 3 times 5, 3 times 8.66. So multipliers can be applied to all the components at once within that vector. However, now that we've got this vector R1 plus R2, now that we know the x and y components of this, usually we don't want to list out the answer as x and y components. X, y components are great for doing calculations. If you're going to be doing any further calculations at all, I would leave everything in x, y components for now. But for the final answer, you usually want to portray the vector in what sort of format? What information do you actually want to know here? Because you can write a vector as x, y components, but that wasn't how it was originally written. What information was originally provided about R1 and R2 individually? Yeah, the magnitude and also what else? Right, magnitude and direction. So typically for your final answer, you want to describe any vector quantities as magnitude and direction. You don't care about how far to the east and how far to the north. You care about how far is it from the origin itself? How far is it away from where you started and in what direction? So ideally, we want to know the magnitude and direction. So let's try that. We want to know the direction. So we usually call that theta. And we also want to know the magnitude. However, we know the side lengths. These side lengths are 8.86 and 9.7. If you know the side lengths, how would you find the magnitude? How would you find how far that diagonal is?
You could do the opposite a little bit. So like for sine of theta would be like 9.7 over the hypotenuse, which you could also solve for with Pythagorean theorem.
Right. The problem is we can't really use trigonometry for the magnitude for the hypotenuse because there's too many unknowns. We don't know the angle and we don't know the hypotenuse, but we can definitely use the Pythagorean theorem here. Because we know that in general, side length squared or leg length squared plus other leg length squared should equal hypotenuse squared. So what we can do here is we can write this as the magnitude squared should equal the x component squared plus the y component squared. And then if we just take the square root of both sides, that should do it. So the magnitude of the vector is just going to be square root of x component squared plus y component squared. Yeah, quadratic formula would be if you're solving something of the form ax squared plus bx plus c. So kind of related, and then they both involve something squared. But Pythagorean theorem should work anytime you're dealing with specifically a right triangle and you know any two of the sides and you're trying to find the third side. So if we punch that into a calculator, 8.86 squared plus 9.7 squared and take the square root, looks like 13.14, about 13.1. So let's round that off to magnitude of R1 plus R2 is about 13.1 meters. And note that that fits nicely into the range that we were looking at earlier. We previously said that we know that it can't be less than 6 and can't be more than 14 as the final result. And we ended up with almost 14 because these two vectors are almost in the same direction, not exactly in the same direction, but they're at least more combining together rather than canceling out. So we've got the magnitude, and we can also find the direction based on, let's say we want to use the two sides we found, 9.7 and 8.86. How do those two sides relate to angle theta? If you're dealing with the opposite side and the adjacent side, what trigonometric function uses those? Yeah, we can use tangent. We can say tangent of the angle is opposite over adjacent. And again, as long as you're always talking about the angle it makes with the positive x-axis, counterclockwise, tangent is always going to be y component over x component. So you can say tangent theta equals y over x. And then how do you undo that tangent function? Yeah, you take the inverse tangent or arctangent of both sides. So that you can just punch into a calculator or again, look up on a trig table. Inverse tangent of 9.7 over 8.86 is about 48 degrees. So that would be the answer here. We would say that that's 13.1 meters in the 48 degree direction. So that's how we would describe the result. R1 plus R2 results in a 13.1 meter displacement vector at an angle of 48 degrees from the horizontal. So that's how you add vectors together if you want the absolute precise results. And of course, you can take this out to as many decimal places as you need. Keep in mind significant figures if that's relevant. And typically you do want to list your answer in magnitude and direction because that's typically the most useful or most meaningful result in terms of knowing where it actually is or how fast it's actually going or how strong a force actually is. But for any calculations, magnitude or x and y components are usually going to be much easier to work with. So in general, when you're going to be doing some calculations with vectors, I would recommend convert everything into x and y components, do all the calculations you need to in x and y components, and then convert the final result back into magnitude and direction. One exception to that is if you're adding vectors that are in the same direction anyway, or exact opposite directions, you can just combine the magnitudes. You don't need to worry about components if they're in exactly the same direction as each other. Alternatively, if you're just multiplying a vector by a scalar, you don't really need the components for that. You just multiply the magnitude by that scalar and keep the same angle. Any other questions on that?
Casey, I had a question about the calculator. So I punched it in and I got 0.83, which doesn't make sense in context. And I was just wondering.
As the angle?
Yeah, I think it's something to do with like tan, inverse tan, or like maybe my calculator is in the wrong setting.
Yeah, you're probably in radian modes, I would guess.
Radian. Okay, so I
Yeah.
can switch that. Okay,
Yeah, so
thank you.
0.83 radians would be the correct answer. And 48 degrees is also the correct answer. It's just two different units of measurement or two different scales for measuring an angle.
Okay, perfect.
So, and check your calculator, make sure you know how to switch between radian mode and degree mode, because they're both going to be useful in both 7B and 7C. We're going to be looking into both degrees and radians.
Okay, cool. Thank you so much.
And there should be a mode button or a settings or something like that. So make sure you can find how to switch between degrees and radians and check which one it's in every time you're going to be working with angles. Any other questions on that? And in general, if you want just some more practice with working with vectors and dealing with the components, I've got a worksheet on that. If you go to math.ncheese.org/P7math, let me put a link to that in the chat, http math.ncheese.org/P7math, capital P, lowercase math. Towards the bottom of that, it's a long list of worksheets. Towards the bottom of the list, there should be one on just trigonometry review in general, if you need some help with that, and another one on introduction to vectors. So just a whole bunch of vectors to split into XY components, a whole bunch more vectors that are already in XY components to put back into magnitude and direction, and some basic vector addition stuff as well. So give that a try. Feel free to bring that into office hours if you need any help with it, and I will see you next time.